Hi, I'm Dr. J, and this is a video about simple linear regression. This video comes after a couple other playlists all about probability and statistical inference, and so you may want to go back and check out those playlists before you try to start on this video. But if you have a solid background in probability, in particular the normal distribution, and statistical inference, ideas like p-values, confidence intervals, and credible intervals, then you should be good to go. As usual, down below there's a PDF version of these slides. Alright, so I want to start out talking about a particular example to try to set some ideas of what we're trying to do with a simple linear regression model. This example comes from the literature, so this comes from a study in the Proceedings of the National Academy of Sciences, and I'm going to read a bit here. I know, terrible for a video, but I want to try to set ideas, and so I'm going to read some excerpts from this paper. So the first thing is that people who are stressed over long periods tend to look haggard, and it is commonly thought that psychological stress leads to premature aging. And in this manuscript, they are measuring aging by decrease in telomere length. They wanted to examine the importance of caregiving stress, that is, number of years since a child's diagnosis of a chronic disease, on telomere length. So we have trying to understand the relationship between this stress and aging through telomere length. The telomere length itself were measured from a DNA by a quantitative PCR assay that determines the relative ratio of telomere repeat copy number to a single copy gene in experimental samples as compared to a reference sample. And the only reason that I need to put this here is because later we're going to see a reference to ratio, and we need to understand that that telomere length is actually a ratio. So let's take a look at the data. So here's the data as downloaded from supplemental material for the paper. So we have on the x-axis the years since diagnosis, the idea being that the longer it's been, then the more stress the individual has been under. And remember, this is diagnosis of a child chronic diagnosis. And so it's the parent's stress in trying to caregive for that child. On the y-axis, we have this telomere length, or that telomere ratio. And so we're trying to look at what kind of pattern or relationship there is between these two. Okay, so that's the plan. What we're going to get to today is basically drawing a line. This right here is called the regression line. And we're going to talk exactly about what that regression line means, how we can find that line if we're given some data, and so forth. That's the plan for today. All right, so here's the model. Hopefully, again, you're used to the normal distribution. If not, you might want to check out the video up here. The simple linear regression model is this model right here. So it says we have observations, y, that is our response variable, and those response variables are independent, and they all have a normal distribution, but the mean depends on an explanatory variable, xi. So the mean for a particular response variable for a particular individual, yi, that mean is beta naught plus beta 1 times xi. And then they all have a common variance sigma squared. Now, if you're coming from a different field, you might have heard different terminologies for this response and explanatory variable. You might have heard outcome and covariate. You might hear dependent, independent. You might hear endogenous, exogenous. So those are all synonyms for these two terms, response and explanatory. Throughout all of my videos, I'm going to try to be consistent and always say response, that's our y, and explanatory variable, that's our x. Okay, so the idea here is that the x is going to determine, the x, our explanatory variable, is going to determine the distribution for y. That's the plan. Okay, so as a visualization of this model, we have a picture that would look like this. So the first thing is that blue line, that's our regression line. So that regression line has some intercept, that's beta naught, and some slope, that's beta 1, and that determines that blue line. Now, at any given value on the x-axis, we have a distribution of possible responses that we could see, and that distribution is a normal distribution, and that's why we have these bell-shaped curves falling along that line. So those bell-shaped curves, the mean is always given by that equation of the line, and then as in this case, the slope of the line is positive, and so as the x variable, the explanatory variable, increases, those density curves, those bell-shaped curves, go up, right? And so the idea here is that we're not expecting all of our observations to fall exactly on the line, but there's some variability that the data have, and that variability is described by these normal bell-shaped curves. That is the normal probability density functions. Now, one of the assumptions that's key in this model is that the variance is the same for all of our observations. And that's why these bell-shaped curves all look exactly the same, right? They don't get spread out or get smaller, right, and more peaked, right? They all have exactly the same spread as we go up. And that's that constant variance assumption in the model. All right, so let's talk a bit about the parameter interpretation. So as a reminder, with that normal model, we can find the expectation for y. That expectation is beta naught plus beta 1 times xi. We can find the variance of y, and that variance is sigma squared. So one of the things we try to do when we're thinking about interpretation of parameters is we try to think of special cases when the explanatory variable has certain values. The first one we're going to think about is what happens when x is 0. When that xi is 0, then the expectation of y is just beta naught. So beta naught is apparently the expected response when the explanatory variable is 0. Then if we think about what does beta 1 mean, what we have to do is we have to think about what happens as x changes. So in this case, we're going to go from a small value little x to a value little x plus 1. And so we're going to calculate the expectation for x plus 1. That's going to be beta naught plus beta 1 times x plus 1. And if we expand that out, we have a beta 1 times x plus beta 1. And now we can determine the expectation when we have just x is equal to little x. And that is just beta naught plus beta 1 times little x. And now we're going to subtract these two. So the first line minus the second line. And if we do that, we find that the difference between these two is just beta 1. And what that means is that the interpretation for beta 1 is that it's the increase in the response for each unit increase in the explanatory variable. Right? And I missed the word there, but it's important. The expected increase in the response for a unit increase in the explanatory variable. So what that means is that as the explanatory variable gets larger and larger, then on average, we expect the response to go up by beta 1 for every 1 unit increase in x. The last parameter I'll talk about here is that standard deviation, sigma. Right? That is just the variability that we expect, right, for a fixed value of the explanatory variable, but it's true for every fixed value of the explanatory variable. All right, so this is just going back to that picture, right? So the only thing that I've changed here on the picture is that I've actually put in the x-axis numbers and the y-axis numbers, right? So the first thing is beta naught. Beta naught is what happens when x is 0. So you find x equals 0 on the x-axis. That's our explanatory variable. You find it 0. In this case, the way that I constructed this, I set that intercept to be 0. So you'll see the blue line crosses y equals 0 right when x equals 0. And that's our beta naught value. Then if we think about beta 1 is our slope. The easiest way in this diagram is to calculate that slope by going over 4, say from 0 up to 4. And we can see that it goes from 0 up to 4 on the y-axis as well. So in this example, that slope is 1. And again, that sigma parameter that we see determines the variance. The variance is constant for all of our values for the explanatory variable. So we have that common shape of that bell-shaped curve for our normal distribution going the whole way. Again, it doesn't get narrower or wider. All right, so let's talk about what happens if you actually had some data and you wanted to find this line that we're talking about. How would you do it? All right, so we are going to rewrite the model in a way that hopefully is helpful, but this is exactly the same model. All we've done is sort of remove the mean. So here we have yi is equal to beta naught plus beta 1 times xi plus ei. And now the ei are going to be independent, identically distributed with a normal distribution with a mean of 0 and a variance of sigma squared. This way of writing down the model is going to be extremely important when we get to talking about model diagnostics. Right now we're going to use it because we're going to talk about these errors, these EIs. And if we just rearrange the first equation, then we get this equation. The EI is just yi minus that line. That is the beta naught plus beta 1 times xi. And now the EIs are the true errors, and we can only calculate those if we know the true values for the line. That is, we know the true intercept and we know the true slope. That is, we know beta naught, and we know beta 1. Of course, we don't know these, which is the whole reason that we're doing the study. And so what we're going to do instead is we're going to, in a second, get estimated values for beta naught and beta 1, and we're going to plug those in. When we get estimates of parameters, we put a little hat on top, right? And so that's going to then give us an estimate of the errors, and typically these are referred to as residuals. So the estimated errors are residuals, although that terminology gets messy in different software packages, but I will try to make that distinction between the two. Okay, we still don't actually know what beta naught and beta 1 are, okay, but that's where we're going. So we're going to get estimates for beta naught and beta 1, and sigma squared for that matter, and we're going to do it through a number of different ways. So we have, hopefully in my previous videos, you've seen methods talking about maximum likelihood, or the MLEs. You've seen Bayesian approaches. This is going to be a Bayesian approach with a particular prior, 1 over sigma squared, and we'll get into more detail about that in a second. But it's also something called the least squares estimators. And I've written down an equation there. We have the sum of the Ri squareds. So when we say the least squares, what we mean is that that sum of those residuals squared is the smallest that it can possibly be. So it turns out that according to all three of these methods, we get exactly the same estimates for these parameters. So the estimates are given by this equation, these equations, really. So we have something, this Sxy over Sxx, that we'll talk about in a second. The slope intercept then can be determined from that slope and the sample average for the response and the sample average for the explanatory. And then we can calculate an estimate for the variance using something called SSE. And you'll notice here that it has a degree of freedom, that's the df, of n minus 2, and you'll see that recurring, right? So in simple linear regression, the degrees of freedom are always going to be n minus 2. Okay, so let's get into what these terms are. Hopefully those y bar and x bar were clear, right? Those are the sample average for the response and explanatory, respectively. This xxy and sxx, right, are basically just sums of squares. And you can see that sxy takes the xi minus x bar times yi minus y bar and sums all those up. Sxx does the same thing but just replaces the y with an x. And then we have the sum of squared errors. That's the SSE. That is just the sum of squared residuals. So it's really the residuals we're squaring because, again, we don't know the errors because we don't know beta naught and beta 1. And so if you actually start, right, getting those sample averages, then you can calculate the sums of squares, and you can go back and you can determine what the beta naught and beta 1 and sigma squared values are. And therefore, you have your point estimates for these parameters. All right. Now, as a visualization of what's going on here is that we're trying to get this blue line. And the way that we try to get this blue line is by thinking about minimizing the sum of the squared residuals. The residuals are the vertical distance between the point and the line. And so you can imagine trying to change that blue line and move it somewhere. You can imagine if you moved it way away from the data, right? Then if you calculate these residuals, they're going to be very big. When you square them, they get even bigger, and you're going to have a sum that's very large. And so you want this line to be sort of in the center of the data points, and there's going to be a unique line that determines, that has the property of having the smallest sum of squared residuals, and it's exactly the line that we found the equation for, that is, we found the slope and intercept for on the previous slide. But the idea here is that we're trying to minimize the square of those red vertical lines, those residuals. All right, now we've got point estimates, and that's fine, but typically we want to provide some kind of uncertainty. And so we certainly we don't believe that these estimates are exactly the true values. That is, we have an estimated intercept and an estimated slope, but those are not the true intercept and the true slope. And so we need to provide some kind of uncertainty about what we believe the parameters to be, given the data that we have. In order to do that, we're going to calculate a few quantities here, and then on the next slide I'll show you exactly how to use them. But usually what we use is something called, typically referred to as a standard error, but I want to point out here it's also the posterior scale parameters. So here we have a formula for the standard error of the intercept. Right? It involves terms that we've primarily seen before. The only one we haven't seen is this Sx squared term. We'll talk about that in a second. We have a formula for the standard error of the slope. It looks similar, but not exactly the same. And now we can talk about what the Sx squared value is. That's just that sum of squared x's divided by the sample size minus 1. We can do the same thing for the y, and we'll see that in a second. Right, where we have an SYY, the sum of squared y's. And so now we have our standard errors, but there's a few other terms that we can actually calculate that are relevant in regression that we can calculate using these quantities. So the first one is the correlation coefficient. So the correlation coefficient can be calculated with these quantities, and that's the same correlation that we talked about in a previous video. Okay, so if you go back to that, but it's just a measure, it's a unitless measure of the relationship between these two variables. We can also square that, and when we square that, there's another representation here. That's called the coefficient of determination. The final quantity that we can calculate is, actually that's in the formula right above there for the coefficient of determination. Right, and so between these two, what the coefficient of determination is really telling us is the proportion of the total response variation explained by our model. In this case, our simple linear regression model, but in future models, it will still be the proportion of the response variability that's explained by the model. Okay, so what can we do with these? We got standard errors, that's great, right? We can now calculate a correlation, we can calculate the coefficient of determination, but in particular, those standard errors are going to be extremely helpful. So if we come at this from a Bayesian perspective, with this particular prior, so now I've written it out sort of fully. So we have a prior on the regression coefficients, beta naught and beta 1, and the variance sigma squared, and that prior is just 1 over sigma squared. Just like with the normal model, this is not a proper distribution, that is, it doesn't integrate to 1, but nonetheless, we can use it to then find a posterior. The posterior here for the individual betas, so the j here means that you can plug in a 0, or you can plug in a 1 if you want the distribution for the slope or the distribution for the intercept. So what we're going to do is we're going to say that the posterior for one of the betas is a t distribution. You notice that its degrees of freedom is n minus 2. That's where that degrees of freedom comes into play. The location parameter is the point estimate for that parameter, and the scale is the standard error. And in my notation, I would typically write in the t notation here that scale parameter squared. Okay, so we can use this posterior distribution to do a number of things. The things that we've done before are to calculate credible intervals. So we just have the estimate plus or minus a t critical value times a standard error. Hopefully you've seen things like this before. If not, go back and watch more of my other videos. And this t now, we have to talk about exactly what that is. So that t is just the value that satisfies this probability statement, where that capital T n minus 1 is a standardized t distribution with n minus 2 degrees of freedom. We can take this posterior distribution and we can calculate posterior probabilities. We can say what's the probability that the parameter is less than or greater than a particular value. In this case, I'm using bj. We just have to do some rearrangement, but now we have a probability statement relative to that standardized t distribution. Now, because the t distribution is a continuous random variable, these probabilities are actually one minus the other one. So if you only need to calculate one of them, and you can get both those probabilities quickly. All right, so that's a Bayesian approach. It turns out that the Bayesian credible intervals on the previous page are confidence intervals, just like they were for the normal distribution. And so the confidence interval here has exactly the same formula. We can also compute one-sided p-values. Those p-values, right, depending on the particular null and alternative hypothesis, right, just change the direction of that sign. But you'll notice here that these two probabilities were exactly the two probabilities that we calculated on the previous slide, right? So those posterior probabilities of a parameter being greater than or less than a particular value are exactly the one-sided p-values. You just have to be careful with those inequalities and getting them in the right direction. Okay, so this is all to say that just like with the normal model, because a regression model is based on a normal distribution, right, there's a correspondence between credible intervals and confidence intervals and between posterior probabilities and p-values. I'm going to talk in a future slide about what to deal with two-sided p-values. That will certainly be important, but I'm not going to put it in this slide right here, or this video for that matter. Okay, so usually software defaults to showing you beta j being equal to 0, because usually that's related to a scientific question of interest. Okay, so I'm going to want to show you now how to do the calculations, but I'm not going to really spend time on it, right? So I'm going to put this here. You can stop the video and you can take a look at it. You can go and find the R code that's on my website and just copy paste it so you can do it. But basically, this is just showing you that if you run through the calculations that I showed you on the past couple of slides to get all the relevant quantities that you need, you can take those relevant quantities and you can construct confidence intervals or credible intervals. You can construct posterior probabilities, right? You can do all those calculations by hand in R if needed. Now, typically, we're not going to do these kind of calculations by hand. I guess before I get there, this slide, oh my gosh, it's huge. This is just to help you check your answers. If you're trying to go through the calculations and you get something not quite right, you can go and check here and make sure that you get them right. Okay, so this is how we're typically going to run a regression analysis in R. The first thing is that we're going to use a function called LM. LM stands for a linear model. Regression is really a special case of a linear model. Then we're going to use the summary function on that object, and it provides us basically all the information we need. The first line just tells you there what you actually called. So it tells you that the telomere length was a response, years was the explanatory, it came from the data set telomeres. The next few lines give you a brief summary of the residuals, so min, max, different quartiles. The next few lines are really the key lines for the estimation of a linear regression model. So we see first that we have a column of estimates. So those are your point estimates for the intercept and the slope. The next column over is the standard error, again for the intercept and slope. That t-value is just the ratio of the estimate divided by the standard error. And if you go back a couple of slides, you'll see that we've had that when calculating p-values and posterior probabilities, if we have beta j being equal to 0. So when I said that software defaults to having beta j equal to 0, that's what I mean. That's that t-value. Then the last column is a two-sided p-value. And we'll see in a future video that that's related to our one-sided p-values. But that last column is that p-value. Then the last thing I want to point out on this summary output is that multiple r squared. Oh, maybe I should. Okay, so the multiple r squared is important. That's that coefficient of determination. And then the line above it, that residual standard error, that is the point estimate for sigma hat, not sigma squared, just sigma hat. And then you'll see here that it has the degrees of freedom. That is n minus 2. So apparently there were, 39 observations. If you want credible and confidence intervals, then you use the conf_int function on the summary, not on the summary, on the model object M, right? And you can get your confidence and credible intervals that way. All right, so once you do the analysis in R, you want to write up the report, say for a manuscript. And so this is the kind of write-up that I would do if it were me providing the analysis. So here I would say something like, telomere ratio at the time of diagnosis of a child's chronic illness is estimated to be 1.37 with a 95% credible interval between 1.25 and 1.48. This is basically an interpretation in scientific language about that intercept parameter. That intercept parameter means, right, the x-axis or explanatory variable is 0. That is the time that the child was diagnosed with a chronic illness. The second parameter, the slope, says for each year since diagnosis, the telomere ratio decreases on average by 0.026 with a 95% credible interval of between 0.008 and 0.045. Lastly, the proportion of variability in telomere length described by this linear regression on years since diagnosis is 18.5%. So still quite a bit of variability that's not explained. Now you can compare what I would probably write up in the manuscript to what was actually written in the manuscript that was published. So this is what we got in the manuscript that was actually published. It said the correlation between chronicity of caregiving and mean telomere length is negative 0.445. Gives us our p-value that's related to the the slope p-value we saw in the previous slide. And it tells us the r squared is 0.198. That was shown in the plot. I will say that these two disagree. I'm assuming that this is because there was some difference in the data that I had versus what they actually used for the paper, even though I tried to download the data from, I got the data from an R package that had the data in it. So perhaps they found an error and needed to correct it post-publication. All right, to summarize this video, we introduced a simple linear regression model. right? So that's just the model here. It's based on a normal distribution. We have a response variable and an explanatory variable. We went through all the details of calculating the quantities of interest. So point estimates for parameters in our model. We got the coefficient of determination. We went through calculating posterior probabilities and p-values and confidence and credible intervals. Now, interpretation, I think, is one of the key aspects or benefits of a regression model. And so I just want to recap that interpretation. So the first is that beta naught, that intercept parameter, is the expected value of the response when the explanatory variable is 0. Beta 1 is the expected increase in the response when the explanatory variable increases by 1. Sigma is the standard deviation of the responses around their individual means. And then R squared is the proportion of the variability described by the model. All right, so I hope you keep coming over to discuss more regression. We're going to move on in future videos to talk about what happens when you have more than one explanatory variable, what happens when you have categorical explanatory variables, what if you don't really want a linear relationship between your explanatory variable and your response. So, hope to catch you in those future videos.